This is the second special discrete probability distribution, which is a geometric distribution. And this geometric distribution can be used to model the number of trials to get the first success in an infinite number of independent trials conducted. For example, if we have to roll a 6 with a fair dice, how likely are we to get a 6 on the first roll, on the second roll, on the third roll, and so on? The way we answer this is using the constant probabilities that are there for success and failure. So, for example, if you want the probability of getting a 6 on the first roll, that will just be getting a success on the first roll, which is 1 over 6. If you want the probability of getting your first 6 on the second roll, that means your first roll has to be a failure and your second roll has to be a success. And so you'll have 5 over 6 times 1 over 6. If you want your first 6, your first success, to be on the third roll, that means you want your first 2 to be a failure. So 5 over 6 times 5 over 6, which is just 5 over 6 squared, then multiplied by the probability of the success, which is 1 over 6. Then the distribution of the random variable x, which stands for the number of trials up to and including the first success that you get in the repeated independent trials. And that random variable x is distributed geometrically. This table here shows the probability that the first success occurs on the rth trial. So for it happening on the first trial, you just need the probability of success straight away. If you want it to happen on the second trial, you need a failure for the first one, then a success for the second one. If you want it to happen on the third one, you need a failure for the first 2 and then a success. If you want it to happen on the fourth one, you need a failure in the first 3, then a success. And if you want it to happen on the rth trial, you want a failure r minus 1 times, then you want a success in the rth roll. The sum of probabilities, remember, this follows a geometric progression, which we learned in Pure 1, where the first term is p, which is the probability of success, and each time you're multiplying by 1 minus p. So that's your common ratio. And to find the sum of all the probabilities, remember, you can go to infinite because they are infinite repeated trials. You will just take your a, which is the first term, over 1 minus r, which is your common ratio. So p over 1 minus p, which just gives you 1. So the sum of all probabilities here will equal to 1. Then these are the following criteria that have to be met for a discrete random variable x to be geometrically distributed. Firstly, the trials that are being repeated have to be independent. They can't be dependent on the previous trial. Next, the repeated trials can be infinite in number, as we said, can go on forever. Then again, like binomial distribution, there are only 2 possible outcomes, your success and your failure. Your failure might have multiple possibilities, so might your success have multiple possibilities, but you simplify them into just being either a success or a failure. And the probability of your success in each trial is constant, is the same. The probability of you rolling a 6 is always going to be 1 over 6, even on your 10th try or on your 20th try. A discrete random variable x, which is geometrically distributed, is shown by this x squiggly line, geo standing for geometric distribution, with 1 parameter, which is just the probability of success. And as we saw earlier, the probability that the first success occurs on the rth trial is just failure for the first r minus 1 trials. So 1 minus p, which is the probability of failure, power r minus 1. Then your rth try should be a success, where r can be any number from 1 up to infinity. Let's take a look at an example. Repeated independent trials are carried out in which the probability of success in each trial is 0.66, correct to 3 significant figures. We need to find the probability that the first success occurs on the third trial. That means you want a fail in the first two, then you want the success in your third one. For that, we will have 1 minus p squared, because you want it to happen twice. Then you'll multiply that by p, where your p is 0.66. So 1 minus 0.66 squared times 0.66. And that will give you 0.076296. That's for part A. For part B, we are told to find the probability that the first success occurs on the second trial or before the second trial. So we can have our success on the second trial, which means the first one is a failure and the second one is a success, or before the second trial, which means in the first trial, which just means directly a success. For the first option, we will take 1 minus p multiplied by p because we want a failure first. So we'll take the probability of failure multiplied by the probability of success because we want the success second. And remember, we can either have this or that. And or in probabilities stands for adding. The second option is probability of success alone, which means just p. This will give us 1 minus 0.66 times 0.66 plus 0.66. This will give us 0.8844. That's going to be the probability that the first success occurs on or before the second trial. For part C, we want the first success to happen after the third trial, which means we don't want it to be in the first trial, we don't want it to be in the second trial, and we don't want it to be in the third trial, which is just 1 minus probability of the first success happening on the first trial plus the probability of the success happening in the second trial, the first success, plus the probability of the first success happening in the third trial. This is just going to give us 1 minus p plus p times 1 minus p plus p times 1 minus p squared. Because if you want it to happen on the third trial, you want 2 failures before having a success. If you want it to happen on the second trial, you need a failure before getting the success. And if you want it happening on the first trial, you need to have a success directly. This will just give us 1 minus 0.66 plus 0.66 times 0.34 plus 0.66 times 0.34 squared. And this will end up giving us 0.039304. That's going to be your probability that the first success occurs after the third trial, which means not in the first, not in the second, and not in the third. Next, whenever we are told to find probabilities that involve inequalities, like how we saw in part B and C in the previous example, we can use these following formulas, where the probability that it happens on the rth attempt or before that will just be 1 minus the failure of the first R trials. Because if you're failing on the first R trials, so in our example in the first 2 trials, and you take those options out by subtracting it from 1, then what you have left with is a success in the first 2 trials, because you are removing the failure in the first 2 trials. On the other hand, if you want the success to happen after the first R trials, that means we just want the first R trials to all be failures. The probability of getting your first success after the rth trial just means you want the probability of the failure in the first R trials. So if you want it to happen after the third trial, that just means you want your first 3 trials to be failures. And we have this simplified with a formula. When random variable x is geometrically distributed, and my probability of failure is 1 minus p, which is also written as q, then the probability that your first success happens on the rth attempt or before it will be equal to 1 minus the probability of failure power r. On the other hand, if you want the probability that your first success happens after the rth attempt, that is just having your first r attempts being failures, which just gives you q power r, because you want the failure to happen r times. Let's look at another example. In a particular country, 18% of adults wear contact lenses, and adults are randomly selected and interviewed one at a time. Find the probability that the first adult who wears contact lenses is one of the 15 interviewed. That means you're finding the probability of your first success happening on or before the 15th attempt. And that, as we just found out, was 1 minus the probability of failure, q, power r, which is 15 in this case. Q here is just 1 minus 18%, which is 82%, so 0.82 power 15. This will give us 0.949. That's the probability that the first guy who wears contact lenses is one of the first 15 people who are interviewed. Then we want to find the probability that not one of the first 9 interviewed had contact lenses. That means we want a failure to happen 9 times in a row. We don't want the guy to have contact lenses. So we want the failure, that's the probability of failure, to happen 9 times in a row, which is just 0.82 power 9. That comes from this formula, because we want P of the first success happening after the 9th attempt. This will give us 0.168 to 3 significant figures, and this is the probability that the first adult who wears the contact lenses is not one of the first 9 that I interviewed. Next example, we look at a coin is biased such that the probability of obtaining heads with each toss is 5 over 11, and thus tails will be 6 over 11. A coin is tossed until the first head is obtained. Find the probability that the coin is tossed at least 6 times. If we want the coin to be tossed at least 6 times, that means we want the first 5 to be failures. Because if first 5 tosses were tails, then he's going to keep on tossing, because he's tossing it until the head is obtained. So if the first 5 tosses were tails, the 6th toss will occur. Right? And he wants it to happen at least 6 times. And so for that, we just want the first 5 to be tails. Therefore, we'll take the probability of you getting tails, which is 6 over 11, and power that by 5, because you want it to happen 5 times in a row, which leads us to having our 6th toss, whatever that is then. If it's heads, then he will stop, but he has done it 6 times. If it's tails, then he'll continue, which means he has done it 6 times as well. This will give us 0.0483 to 3 significant figures. That's for part A. For part B, we're told to find the probability that the coin is tossed fewer than 8 times, which means we want the probability that the success happens in the first 7 tries, which means the probability happens in the first 7 tries. Why 7? Which is the probability that the success, which is getting the head, happens in the first 7 tries. Why in the first 7 tries? Because if you get the tail on the 7th try, then you're going to keep on tossing, which will take you to your 8th try. But you want it to be fewer than 8 times. So you're going to take the probability of your first success happening on your 7th try or before that, which will lead us to us having fewer than 8 times. This will just equal to 1 minus q power 7. Q in this case is the probability of getting tails, which is your failure that you have decided, because your success is your heads. And this will just equal to 1 minus 6 over 11 power 7. This will give us 0.986 to 3 significant figures, which is your probability that the coin is tossed fewer than 8 times, which means we get head because that's when we stop tossing in the first 7 tries. We then go into the mode of the geometric distribution. Now, all of the geometric distributions have 2 features in common. Firstly, that the first try has the greatest possibility of happening, the greatest probability rather, and the probability decreases as R increases. Meaning, if you want your first success to be somewhere further on from the first try, it keeps on getting lower the further you want it, the probability we are talking about. As you can see here, we have 2 examples, one with probability of success 0.2 and the other one probability of success 0.7. And both of them, as you see, the probability reduces as the R increases. Same here, the probability reduces as the R increases. Meaning the first attempt is actually the attempt with the highest probability of you getting a success. Then we go and look at expectation. We know that when you look at a discrete random variable, the expectation is the sum of all the data points times their probability. When you do that in the geometric distribution, the expectation of the discrete random variable, which is geometrically distributed, is going to equal to 1 over p, where p is the probability of success. So the expectation or mean of the geometric distribution is a reciprocal of your probability of success. And a proof of this is shown in this YouTube video, which will be linked below. Let's now look at a few examples. 1 in 4 boxes of Zingo breakfast cereal contains a free toy. We need to let the variable x be the number of boxes that a child opens, up to and including the one in which they do find their first toy. So not all of them have toys. We have to find the mode and the expectation of x. So the mode of any situation where the discrete random variable is geometrically distributed is 1. Because the first attempt being successful is actually the most likely to happen in terms of which attempt gives you your first success. And so the mode just equals to 1. When you look at the expectation of x, as we said, expectation of x is the reciprocal of the probability of success. And in this case, the probability is 0.25. So 1 over 0.25, which just gives us 4. So our expected first toy will come out in the 4th try. Now let's just explain what these two mean. That's what part B is about. We have to interpret the 2 values that we found in part A. So what mode means is that you are most likely that it happens on the first try. Meaning the toy is most likely to be found on the first try, because that's the mode. However, on average, a child finds the toy on the 4th attempt. There's a big difference between these 2 values here. Next example, another expectation and mode of a geometric distribution. We're told that a discrete random variable x follows a geometric distribution and we're given that the expectation is 3.5, and we're supposed to find the probability that our discrete random variable is greater than 6, meaning the first success happens after the 6th attempt. For that, firstly, we need the value of p. And how do we find the value of p? From the expectation, because expectation is equal to 1 over p, which is equal to 3.5. Therefore, p will just equal to 1 over 3.5. Therefore, p will just be 2 over 7. That's the probability of success, and as a result, the probability of failure will be 5 over 7. Then, when we want to check the probability of a discrete random variable being greater than a specific number, meaning we don't want the success to happen in the first 6, which means we just want failures to happen in the first 6 attempts, which will mean that you want failures to happen and happen and happen and happen consistently 6 times. And that will give us 5 over 7 power 6 as a probability that the first 6 are all failures. And that will just give us 0.13281 and so on, which into 3 significant figures will give us 0.133. Next, we're given that x is geometrically distributed and that the probability that x is lesser or equal to 3 is 819 over 1331, and we're told to find the probability of the discrete random variable x being greater than 3. That is quite simple because this is just the complement of this. Because if something is not lesser or equal to 3, then it is going to be greater than 3. So if you don't get the success in the first 3 attempts, you're going to get the success after the 3rd attempt. So they're complements, and so probability of x greater than 3 will just equal to 1 minus 819 over 1331, which will just give us 512 over 1331. That's going to be the probability that the discrete random variable gets its first success. That's going to be the probability that the discrete random variable is greater than 3, meaning the first success happens after the 3rd attempt. That's part A. For part B, what they're saying is that they want the discrete random variable to be between 1, but not including 1, and 3, including 3, which is just what this is, but excluding 1, meaning you don't want it to happen in the first attempt. And for that, we're sort of going to take p of x is less than or equal to 3 minus p of x is equal to 1, which is just going to be 819 over 1331 minus p, because you want the first probability to be 1 of success, because you want that first attempt to be successful straight away. That's what this means right here. But for that, we need to find the value of p. And the only information that we have been given is this, and we found this as well in part A. So we can use one of them to get the value of p. So suppose we use the answer we got in A, where we find the probability that the random variable x is greater than 3, which means the first 3 attempts are failures. The one after the 3rd attempt is a success. So we want the first 3 to be failures, and therefore p of x greater than 3 is just equal to q power 3, the failure probability happening 3 times in a row. And that will equal to 512 over 1331. Then if you want to find the value of q, just cube root both sides, and you get that q is equal to 8 over 11. And because q is equal to 8 over 11, p here will be 3 over 11. Therefore, what we have is 819 over 1331, which is a probability that the discrete random variable x is less or equal to 3, subtracted by 3 over 11, which is the probability of the discrete random variable equals 1, which as a whole gives us the probability that the discrete random variable is less than or equal to 3, but also greater than 1, meaning it's excluding the 1. And this will just give us 456 over 1331 as our answer. And this is the summary of differences between the binomial and geometric distributions. There's not that much difference between them. It's the same trials happening, it's the same criterias. However, the one big difference is the number of trials. So in a binomial distribution, you have a fixed number of trials, and your discrete random variable is the number of successes in those trials. In binomial, the discrete random variable is the number of successes in a specific number of trials. While in a geometric, the discrete random variable is the trials that are repeated until the first success occurs. And as a result, in a geometric distribution, there is no fixed value of n. So if the discrete random variable x is equal to 2 in a binomial, and a discrete random variable x is equal to 2 in a geometric, obviously in a binomial we need a value of n, which is the number of times you repeat the trials. Suppose that is 5, n is equal to 5. What this specific scenario means is that out of 5 tries doing that experiment, 2 of them were successes. While in this, it means we did 2 tries to get our first success. That means our first one was a failure, that's why we repeated it, then our second one was a success, and we stopped it, and that was our discrete random variable value. And finally, the expectations and the variances for all of them are also required to be known.